So this first part is just going to be a review of what we did a few days ago. You recall when we want to make a graph of an inequality, we'll either choose to use a dashed line or a solid line depending on if we use the strict inequality or if we have the inequality with the equal sign in there. And so then what we do when we take an inequality like y is less than or equal to 2x, we do have the equal sign part of the inequality up here. And so we're going to graph this as the solid line. And then what we'll do is we will we'll choose a test point that's convenient, and 0 often is pretty convenient. So if we use 0 here, we'll say 0 is less than 0 plus 1. And so we get 0 is less than 1, that's true. So then the side that the 0, 0 is on is the side that we're going to shade. Otherwise we would shade the other side. And so we would get a graph that looks something like that. Okay? I think you all did pretty well on doing this, as I recall. So what we're going to do now is that we're going to look at systems of inequalities. And so the basic tools that you're going to use are going to be the same. What we're going to assume is that all of these inequalities have to be true all at the same time. And that's why they would be a system of inequalities, is because we're having cases where we'll have more than one of these inequalities, but we want all of them to be true. So let me show you what happens here. So if we have this, this one system where we say x plus 2y is greater than 4, we get this, we get a graph that looks like that. And if we take another equation, say 2x minus y is less than 2, this one is going to look like that. So then when we put them on the same graph, both of them involve the lines, but there's only one region where both of them are going to be true. You see, you look at the one on the left, all the blue, it's above that line, and then the one with the green shading, everything to the left of that line is true. So it just turns out that this region up here is the only place that it's true. And so what we're going to do is use two or more equations, and we're going to draw these lines and figure out where do all the true regions intersect. And so there's a couple approaches to use on this, and some of them involve using an eraser, so you graph one and then you erase the region that's not true with the other one, or what the current Math 3 book uses, the finite math, is that they will shade the false side and see what gets left unshaded as being, you know, the section that's true. But the one that I'm going to choose to do involves using little arrows on our lines. So let's say we have this equation, x is greater than or equal to 1. So I'm going to draw my first line. So this is my x equals 1 line. And then I'm going to put these little arrows on the ends of my line that say it's going to be, the true side is on this side. Okay? So I'm just going to keep these here, and if you like to be really nice and clean, you can go back and erase these when you're done. But let me put a few more lines on here. Like, let's say I want x is less than 4, so I'm going to draw my x equals 4 line. I'm going to make it dashed because that's a strict inequality. And then I'm going to put my little arrows that say, okay, it has to go that way now if I were to shade it. Make a couple with y. So if y is greater than or equal to -3, I draw my line at -3 here. And then I notice that in order for y to be greater than 3, that would be everything above that line. And then I'll take another similar line to all this. Y is less than 2, and notice that I have my arrows pointing down. Okay, so now what I do is I look at all my arrows and say, what regions are true? And when you have all these lines, you're going to end up with, you know, regions that maybe two of the lines are true, like where my pointer is right now, both of the y equations are true, but not the x equations. Or if I go up to here, both of the x equations are true, but neither of the y equations are true. So by inspecting the direction of my arrows and everything, the area that's going to be intersecting all of them is going to be this, this rectangle in the middle. So then that's what I'll choose to shade, and I get something that looks like that. So here's four equations, four inequalities, and they're simple. And there's this rectangular region that says this is where my solution is. So if I were to choose a value in here, like let's say if I were to choose this point right here, so x equals 2 and y equals 1, okay, every single one of these would be true. Well, 2 is greater than 1, 2 is less than 4, y is greater than, or 1 is greater than or equal to -3, and 1 is less than 2. So each of them are true, and so we get this nice region. So to check yourself, you should do this, where you say, okay, here's the colored in region, choose a point, one that's easy to read, and plug it into all your equations and see if they're all true. Now that doesn't guarantee that you've put in exactly the right area. If you extended this into areas where it's not true, then you would have to discover those by going into those regions. But generally, if you start looking at your arrows and seeing, are all these things true here where the direction of my arrow is concerned? So this dashed line is a boundary, and the boundary that has the solution on it is this side of it. You can kind of reason through these. Now, I don't mind if you leave those little direction arrows on there. If you want to make a really nice, pretty, polished graph, you'd probably just go around and erase them just to avoid any kind of confusion there. All right, so let's take some lines that aren't necessarily horizontal or vertical lines. Here we have x minus 2y is less than or equal to 4, x plus y is less than 3, and x is greater than or equal to 0. Now, having more than two equations is of course possible, and it's common. Oftentimes you'll have these kind of equations that says x has to be positive. All right. So if you're looking at let's say a combination of things like there's a classic problem called the diet problem of what is the lowest cost diet that you can have by eating from among these foods. And so it lays out like something like this, because you can eat, you have to eat certain minimum levels to get vitamin C and vitamin E and all that kind of stuff. You're going to eat a positive amount. You're not going to eat negative amounts. So one of the natural boundaries that comes into a lot of these kinds of problems is that x or y or both of them have to either be true or have to be greater than 0 or less than 0. So those are really kind of natural inequalities that show up on these graphs. Okay, so let me graph this. I'll make my axes, and the first one is going to look like a line, and it's going to, so I have the x minus 2y is less than or equal to 4. And remember how you can graph these with both of the variables being on the same side. When x is 0, y must equal -2. So that way I have my intercept on the y-axis. And then when y equals 0, x is equal to 4. So there's my intercept on the y-axis. Now if I choose my point of 0, if I have 0 minus 0 is less than 4, that's true. So I put my arrows to indicate that that side of the line is my true side. Then I do the same process with the next one. And so x plus y is less than 3. So when y equals 0, x equals 3. And when x equals 0, y equals 3. So I have this line. I'm going to choose my point. My test point is 0 again. And so I say 0 is less than 3. So here I have my line showing up, my arrows showing up on this side of the line, indicating that this is the region where this is true. Now when x is greater than 0, that means that everything to the right of the y-axis is going to be part of the solution. So I can put put arrows there to say, that says, okay, everything on this side of the y-axis is part of the solution, and when I inspect my arrows there, I find that my shaded in region is this region right in here, and so there's the complete solution. So if I were to check something, I would choose a point, and probably a real nice convenient point here is perhaps 1 and 1, so x equals 1, y equals 1. So if I have 1 minus 2 is less than 4, that one's true. 1 plus 1 is less than 3, which is true, and then 1 is greater than 0, so it's true. You can test all these things fairly deliberately. So this isn't too different from what we've done before with graphing inequalities. It's just having an eye on when are they all true. So of course, here's one for you to try. Okay, well, let me just continue with this then. So if we have our axes here, the first line is going to x plus y is greater than 4, so our two intercepts are going to be 4, 4, 0, and 0, 4. And it's going to be greater than, so if you pop in the origin, 0 plus 0 is not greater than or equal to 4, so it's going to go away from that line to the right. Same thing with the second one, where the intercepts are 2 and 8, and so we find that those go above. Now with the x and y being positive, you know that it's going to be this quadrant only that you're going to have some shading. So this quadrant is not going to be shaded. This quadrant doesn't have any shading, nor does this quadrant. So if we go ahead and start shading everything, you get something like that. Yes?
What's the shading on the top again?
I'm sorry now?
Why is it on the right?
Why is it here?
Yeah.
Because this line here, let me, I'll back up a bit. That line there, you understand that this is the solution side, right?
Yeah.
Okay, and then when I put in this line, this is the solution side as well. Now, if I suppose I can do this, that if I look at my axes, this is the solution side for x is greater than 0, and then this is the solution side for when y is greater than 0. So you look at everything that's pointing there, and so all of these have to be true simultaneously, so it's just where all these things overlap, and that's just going to be that area above it. So all of the points that are within this region, you see all my arrows point to that direction. When I'm here, say for instance, it's true that x and y equals 0, but the other two equations don't hold. Okay?